Are you guys ready? So far we have learned that light, which travels like a wave, can sometimes act like a particle. So that was just something that completely turned everything on its head. So this scientist named De Broglie came along and said, well, okay, so we thought light was this one thing forever. So, but then it actually can act like a particle. So what if the particles that we know about can act like waves? Do they have wave properties? And then he was able to mathematically back that up and say, well, we figured out that photons have momentum, right? The momentum of a photon is h over lambda. But we also know that momentum of a particle is equal to mass times velocity. So if I make these two things equal each other, I could argue that mathematically something with mass has a wavelength, right? And we can calculate that wavelength using this equation. So we know at least mathematically we could possibly think of something that has a wavelength, that a particle that has mass, could it have a wavelength? So we did start to do some experiments with this. So how do we know things act like waves? Well, we do something like the double slit experiment where there's diffraction, right? We know waves disperse around a smaller opening. So of course we're going to do that with particles and see if the same thing's happening. And then we can see if it travels as a wave. So at this point, I need you to stop listening to me because I can make it sound as cool as I want, but there's no way I can make it as good as this video. I will also include the link to it down below. Seriously, you have to stop the video right now and go to this one with the double slit experiment with Dr. Quantum before moving on, because I'm going to be referencing it a ton now. Okay, so pause the video, go watch that one right now. Is your mind blown? So let me just go over what that video said again. So we had an electron shot at a double slit, right? It's really, really, really small double slit. And it demonstrated the fact that it acted like a wave, at least when we weren't conscious of it, when we weren't, trying to watch it. And then you're watching it and it is acting like a particle again. Like, are you kidding me? So this is really the start of and you're going to ask me why. I do not have the answer why. No scientists have the answer why. Why do electrons do this? We still don't actually know. So this is just really the start of just new science and where physics is going today. So when we look at this electron going through a double slit, we can see that it can have these wave-like properties. It can make interference patterns. And that was happening. The electron was still acting like a wave even when it was being shot one at a time at the double slit. So that is just completely insane when you think about it. So of course the electron is just this really, really tiny particle moving at really high speeds, and so it can be detected. It can act like a wave. So that's really important to know, that it's something with a really small mass moving at a very high speed. Okay, and so then that electron that's a really, really small, moving at a very fast speed, can be diffracted and can interfere and can act like a wave. But also we do need to say that electrons' wavelengths are typically thousands of times shorter than visible light. So really you do need to have a microscopic lens to be able to see their diffraction pattern. But because the wavelength is so much smaller than visible light, it actually can distinguish more detail in certain microscopes. So I don't know if you've ever heard of electron scanning microscopes, but this is using the fact that electrons can travel as waves, because then they can have this electron detector next to something, when you're looking at something that's really, really, really small, and the wavelength can pick up on the different smoothness of all the different surfaces. So you can actually get way more detail in something that's really, really small using an electron scanning microscope, which is basically using an electron as EMR, as light, which is really, really cool. But of course, it's not traveling at the speed of light because we can't get electrons to do that, but it's still traveling really, really fast. So this is kind of the setup of a scanning electron microscope, which I'm not going to go through with you right now because it's just not something we necessarily need to know. But that's something you've probably heard of before, and that is using the fact that electrons can act as waves, which is really, really cool. So here's a few images from a scanning electron microscope. And try to take a guess. I think you can tell what that one is. That is a snowflakes. Okay, so again, it just gets that incredibly close-up detail. Any guesses what this is? That's salt and pepper. So again, it just gets it in such more fine detail than anything else, than any other EMR that we can use, because the wavelengths are so much smaller. This is a deep ocean worm, which I know is just weird looking, but it's a funny picture, so I'm just going to keep it in here. Okay, so let's go back to that experiment that was performed that scattered the electrons, that helped us figure out, oh my goodness, they can travel as waves. So the electrons, again, they scattered into pattern of regular peaks, which means, that's their constructive and destructive interference. And then when you saw the peaks as the diffraction pattern, well, the wavelength matched the one that de Broglie predicted, right? With putting his two momentum equations together. It completely matched up with this equation here. This lambda is equal to, darn it, what was it? I already forget. H over mv. Okay, and so if you took the mass of an electron and the velocity that it was traveling at, you were able to figure out its wavelength, right? Which is why really, really, really small masses are the only thing that's really going to give us a wavelength. Something with a bigger wavelength, a bigger mass, well, you're going to be taking h, which is a really small number already, and dividing it by a bigger number. So it's just going to be way too small for us to really get. But when we divide something by a really, really small number, we get a much bigger number. And that's why we can still detect wavelengths of electrons, because they are just so small and so, so light. So of course, as you probably saw in the video, what happens is if we just shoot those electrons one at a time at the double slits, they just make this diffraction pattern. And here, this is, if there's just 40 electrons, then it's possibly could be misconstrued or thought to be something different going on. But, you go up to 200 electrons and you really see, oh yeah, it's making, those are the bright spots. And you keep doing it for a long time, and it's very clear we have our constructive interference and we have our destructive interference in between. And this is just so clearly a wave pattern, and just showing us that, yes, electrons can travel as waves. So this actually helps explain the orbits. Remember the orbitals of Bohr. So I told you that's actually not true. Electrons don't actually travel in these nice circular planetary orbits around the nucleus. When we actually watch them, we can't quite tell what they're doing, but this explains why that they can only be in certain energy levels. Because the orbit exists where the electron wave is in phase with itself. So basically, it's when it has constructive interference. So when something like this is happening, when you can have perfectly, 3 waves or 4 waves or 5 waves or 6 waves, And that is why an electron can only inhabit certain energy levels. Those energy levels, they're not actually, this perfect radius that they're going around like this. They're not necessarily moving like this either, but it's just the fact that at this point when they're in the atom, they are kind of acting like waves. And so it's when they're in phase is when the next energy level will happen. Because if it's not in phase, you get something like this where they don't really line up. And of course, that just can't happen. An electron just won't allow that to happen. So therefore, it can only be at a certain energy level, what we call the energy level, because those energy levels are describing when the electron is in phase with itself. And it can't be anywhere in between because it's out of phase. That's when it has destructive interference, and then if the electron were to be at any place in there, that's when it would collapse in on itself. So the cool thing about this is it explains so much about Bohr's energy level, because even though they don't travel in these nice planetary orbits that are perfect circular things, like, around the nucleus, we still know why that's such an important model of the atom, because it actually still does have a lot of value to us, and it does tell us a lot about the current model of the atom and why it still works to, think of these orbitals. Okay, so when you look at the orbit circumference that Bohr had, that's really just the multiple of the electron wavelength. And then since those circumference of orbits are discrete, meaning they only happen at certain levels or certain values, then those energy levels are also discrete. So that's basically the explanation as to why Bohr's model still really works and something that we really need to think about. Because, of course, when the electron's in phase, it's allowed to orbit kind of around this energy level, or at least could be contained in this energy level. And then anywhere in between there, it wouldn't be in phase until it has, 4 wavelengths, and then it can be in phase again. And that is exactly why electrons have energy levels around an atom. So there you go. I know it's kind of crazy if you're like questioning everything you've ever known in the world. That's okay. You're supposed to right now. That's what this whole lesson is all about. So there you go. Good luck with that. Have fun. Hopefully you're not having like an existential crisis yet. If you are, just, email me, let me know. Also email me and let me know if you have any other questions about this. But that's it for me today. So good luck with all this and with completely changing your entire worldview. Bye.